Okay, it's time to start. And I would like to say hello and welcome to a webinar dedicated to drone-based GPR in general and the MALÅ GeoDrone in particular. My name is Andreas Wiberg and I am the product manager of the MALÅ GPR range of products. And I will start this webinar with a short introduction and then hand over the presentation to my very capable and knowledgeable colleague Jesper Emilsson. The content or outline of the webinar looks something like this. As I mentioned, I will start with a short company presentation to provide you with a very short introduction to Guideline Geo, who we are and what we do. The rest of the webinar will be based on results presented in an article published in the journal First Break last year and will take you through both practical and theoretical considerations for drone-based GPR. It will also provide you with the results from a few case studies, which was all included in the article. And of course, in all the examples, the MALÅ GeoDrone antennas have been used for the data collection. Before we move into the presentation, I would just like to mention that you all have the opportunity to ask questions during the presentation. Just add them to either the chat window or the Q&A window, and we will circle back to them in the end of the webinar during a short Q&A session. We will also upload this webinar to the Guideline Geo YouTube channel, so if you have missed part of the presentation, you will have an option to catch up at a later point. Again, a warm welcome to you all, and let's begin. Guideline Geo are world leaders in geophysical solutions, and we have been so for quite some time. We are celebrating our 100-year anniversary this year and have many exciting things to share with you in the coming months, which I really look forward to. Our products are both developed and manufactured in Sweden, and apart from Sweden, we have a very strong global reach through our different offices around the world and our extensive distributor network, which currently covers around 90 countries around the world. And this brings us close to our customers, and we have a very close collaboration with both customers, universities, and partners. As you can see from this map, we have a number of different offices around the world where we have Guideline Geo staff, from Kuala Lumpur in the east to Salt Lake City in the west. Myself, Andreas, and Jesper, we are currently situated in Umeå in northern Sweden, where we have the development office and the R&D. What's not visible in that map is our extensive list of distributors. And we, as I mentioned, covers around 90 countries around the world. And Guideline Geo, it's consists of two different brands, Airborne, which manufactures and offers resistivity, seismic, and TEM instrumentations, and MALÅ, which we're going to talk about today, which is the GPR or ground penetrating radar manufacturer brand. We have, as I mentioned, a very close collaboration with many different partners and customers across the globe. And this list is just to highlight a few of them. We are constantly engaging in new collaborations, and the list is ever growing. And of course, it's not only restricted to companies, but also to academia and to universities. And also here we have a short list of a few of them that we have collaborated with in the past and are currently collaborating with. Okay, that concludes my short introduction. And with that said, I would like to introduce you to my colleague Jesper, who will continue the webinar going forward. Jesper.
Thank you, Andreas. A very nice introduction, I must say. I was running the slideshow so far, and I had a hard time to keep up with when to change the slide. But I think it was working okay, I hope. So why Airborne GPR? And that is a very relevant question to ask, because anyone who has been working with GPR knows the benefit of keeping it close to the media that you are trying to investigate. There are many advantages of that. An air-coupled antenna adds complexity, and that is one of the challenges when you make a GPR antenna airborne, or when you try to collect from the air, like in this case. And we have had, I would say, at least the last 10 or 15 years, requests for developing or building airborne GPR solutions, and we have not done so until, I think it started maybe 4 years ago, 4 or 5 years ago. And it started as a consulting project. It was basically an offer we couldn't say no to. We did this. It was interesting that we thought the application was doable. So we started doing this together as a collaboration project together with a very big customer to us. In general, there has been a large interest for unmanned geophysical investigations in general. I think that most of us that are in geophysics, we can see this trend. So not only airborne, autonomous unmanned geophysical investigations in general is on the rise. The challenges, of course, when you make a GPR antenna airborne is that you add a lot of technical challenges, but also various regulations needs to be addressed. There is both regulations regarding flying airborne drones in most areas, and also the use of GPR, especially if it's airborne. It also affects penetration depth and resolution. We'll get more into this later on in the presentation. There are, of course, advantages, otherwise we wouldn't do it. It's not just fun. It is fun too, but there is some other advantages besides being fun, and that is that you get access to areas that would be hard otherwise to do surveys in, inaccessible areas. It's also very fast. You can collect data, especially in difficult terrains. You can, an automated survey and by air, you can collect data. So there are a number of, it's not possible for all applications, not yet at least, but it's suitable for certain applications. And in the ones that we have been involved in, we could say that these are, being where we are, snow and ice in general, glaciology, crevasse detection, snow taxation, looking at snow loads on roofs, anything with snow and ice are usually good. Bathymetry, that's the co-project that we started with, looking at floodwater management, and we're looking at shallow sediment studies, depth to bedrock, etc. It could be, there are possibilities to solve that as well. Large cavities and sinkholes, another application, and peats and bogs. There are more, but those are the ones that we have done some work in at least. And I will start this presentation by showing a few examples from projects where we have been partially involved at least, glaciers. We have collected data in Scandinavia, Greenland, Alps, Himalayas, and Antarctica, all over the place. And with this GeoDrone example is taken from the Rhone Glacier. This study was done by ETH Zurich, and they were looking at the depth of the formation and other structural information as well. This data looks really good, I would say. We did some development for this project, and we reached down to above or more than 100 meters depth at least. We could see the bedrock at this depth with very mild processing too. We used the MALÅ GeoDrone 80, which is the only officially released product as of yet, even though we have been dabbling with other frequencies also, which might or is likely at least to result in some other frequencies built on the same concept. The next example is bathymetry, also widespread use, and this example is taken from this US European co-project where we were involved developing the tool. And I think this data is from northern Sweden. It's a river crossing, and the bottom profile. Other areas that we collected data in was mainly in North America, and it was basically to estimate the moving water volume. The next example is from peat study. That is a source of energy, and that is to estimate the volume of peat that could be explored. This data, as you can see, actually I think this picture in the background is from the area, so you can see there are quite a few trees here, and you can also look, if you look in the top picture on the data itself, you can see that there are reflections from above ground, deeper down in the data set, and that is one of the things that makes interpreting data sometimes a little bit harder. If you do a good job, you can deliver a result that looks something like the picture below, which is a color-coded map with the depth in deeper depths in green and more shallow in red. Snow depth. We were contacted by a large company, a large vehicle manufacturer here in Umeå that has a facility that a large factory area. You can see it in the back as well. That's a picture from this actual industry, and it has a lot of flat roofs. And if the snowfall is great during the winter time, the snow load can be very large, and therefore that's something we need to monitor if you have a flat roof. So they wanted to find an easier way to cover this area, and we did some trials with MALÅ GeoDrone, what we called 600, which is a 600 megahertz antenna, to collect this information from the rooftop. The data shows the snow surface. We actually put out some flat metallic, I think it was just a plate that we put on top of the snow in order to see exactly where the snow volume starts, because that can be an issue if the snow is very light and very dry. It's sometimes hard to see that first top reflection from the snow layer. In this case, it was fairly clearly anyway where it was, but that's at least an indication on what it looks like when you have markers put out. That was the 4 examples. And if we then talk about general technical challenges, we are not going to touch on the regulation issues. But I would like to say and stress that if you're using airborne geophysics or GPR in general, or drones, make sure that you follow the local regulations and make sure that you know them, because there are some that you need to pay attention to if you do this type of survey. The general technical challenges that we will talk about this time or today is the footprint widening that happens when you raise the antenna above the surface. We will talk about unwanted above ground reflections and about power loss caused by a surface reflection. We start with the footprint widening, and this is then compared to ground coupled measurements or ground coupled data. You will see that you have a larger footprint, which will in some way, in some form, will result in less resolution. And there will also be horizontal smearing that will make it harder to detect point objects. If you look at the little sketch that is done here, you can see the antenna on top. That's the drone altitude. It's just a tube, and then just dipole antenna there, and then you have the ground surface, and that's where you normally would and then there is, below the drone altitude, there is the ground surface, and then you have a target depth below that. And normally GPR would be conducted on top of the surface, of course, and then the footprint is here represented by by the orange cone or the orange area below at the target depth. If you raise the antenna above the ground, you will widen this footprint at depth, and that is represented by the yellow area. This difference lessens with depth, but it increases with permittivity and elevation. The relative dielectric permittivity is so, for instance, when it's higher, so for instance in water, you would see this becoming a little bit more of a problem, but in a dry area it would be less of a problem. The unwanted above ground reflections is something that you can't really get away from, but if you look at the picture on the right here, in this particular case where we are collecting data across a river stream, that is, it doesn't really come into play because you don't really have that much above ground that you can reflect off from. But if you have the case, for instance, from the peat measurements that I showed earlier, where you have trees, this will become a problem. You can reduce this effect somewhat with filtering, and we did a few. We have done some tests on this to FK filtering, and you can see this data contains some unwanted air reflections or above ground reflections, and after the filtering we can reduce that to a certain extent. You can't really get away from all of it, but you can at least do something little about it. The third challenge that I listed before is the power loss caused by surface reflection, and of course that happens, that will always happen, but how large is it really? From the highest loss you will see also at high RDP values or relative dielectric permittivity values, but it's never more than 10% of the maximum output power. We did practical tests with just raising the antenna and collecting data from the same area or same line, and you can see these are the results from 0 meter above surface, 0.5 meter above, and 1 meter above. And there are other things in this data. I actually think that the 1 meter data looks astonishingly good, while the 0.5 meter data, it looks at least more ringy. That of course has to do with it has to do with the center frequency that you're using in the antenna itself. Okay, the last part of this presentation I will spend on looking at a case study we did last year together with a major, the largest energy provider in Sweden, that is Vattenfall. And they contacted us to see if we could help them find a method with how they could monitor in a better way than what they are doing now, because they are monitoring the ice buildup around the hydropower plants already, but they want to find a more efficient way of doing so. Why is this important? Because it can and it affects the production of electricity in cold climates. So there is always an amount of ice building up around the power plant itself that might reduce how much electricity that can be produced at one point. This resulted in a study and an abstract that was submitted last year to the Near Surface Geophysical Conference. So where did we do this? We did this at Stornorrfors, which is a fairly large, at least as far as how much power it produces. It produces 2.256 gigawatt hours annually. And so it's one of the more important hydroelectric power stations in this country, where we looked at two areas of this site. We looked at spillway, a little bit north of the major intake, and we also collected some data at the intake. We we tried to evaluate the MALÅ GeoDrone solution, and we created this higher frequency for this project in the 600. So at each locale we did a lot of different flights, but these are the major ones, and we also repeated some lines in order to look at the repeatability of the study. We intended to use a navigational software with a pre-planned route planner. We had some issues with this because the unit, we wanted it to be as low as possible, and it didn't want us to go as go too low. In the end, it worked out fine. So, and it's highly recommended if you're doing this type of service to use some type of navigational software. At least if you are, well, I'm not a professional drone pilot. You could use that too, I guess, but it still would help to have a navigational software where you plan your survey in detail. The flight elevation, we try to keep it sub 1 meter. We had some issues with loss of positioning data at the intake locale, so most of the data presented later on in this presentation will be from the spillway. The method or the equipment we have been using is the MALÅ GeoDrone 600. You can see it depicted and to the right. Vattenfall had their professional team of drone pilots that did the survey for us. So they were using a DJI Matrix 300. For positioning, we used the built-in SBUS DGNSS positioning solution that is integrated with the MALÅ GeoDrone, and that is probably the area where we could do better. I think we'll get to what we can do better in the summary later on. We used MALÅ Controller app, which is connected through Wi-Fi to the MALÅ GeoDrone antenna, and we did a upload of our data securely to MALÅ Vision for processing and visualization. I think most of the data is presented as screenshots from MALÅ Vision in this presentation. So let's go to the field, and I collected a few videos just to give you a feeling for what it looks like being there when we were collecting data. I don't know if you can hear sound, but there is nothing important to that anyway, but it's always fun to have sound, right? So the first little video clip is from one of the liftoffs that we did at the main intake. And then the second one was basically when the navigational software kicked in and started putting the antenna into position. We weren't really interested in measuring where there was open water, but this was the best video clip of the ones that I had, so I took this one just to see it in sort of more in action. So, and then what did the data look like? This is a picture from the spillway, and the data quality was at average. It was good. I think both spillway and the intake were good, but the spillway was much clearer. As you can see, this example is from the spillway. It's easier to make the interpretations at the spillway than it was at the intake. That's understandable because at the intake you have a much faster flowing water, of course, and so the ice will tumble and it will break and it will cause not as good response. The data was calibrated using ice core samples. We had this is some raw data, and that's an example of a core sample, and we could then fairly easily interpret what was ice and what is water or snow. The velocities we measured, we calibrated the equipment as we were collecting the data. We ended up with around 165 to 170 meters per microsecond, which is pretty much what what was expected. We didn't do much processing. We did some corrections. Of course, we have to, since we're collecting data on time, it's time triggered data. So we need to use the integrated GPS information to get a length axis for the profile data. We did a bit of band passing and just plain gain. This is a different way of looking at the results. The spillway, we saw that the ice thickness was between 40 and 92 centimeters. At the intake, anything from 0 to 65 centimeters. And if we compared our data to the course that we took, the ice course, the manually cored areas, we saw that there was a deviation around plus minus 5% from true values, which was better than I had expected. We had low deviation at spillway, a little bit higher at the intake, where the ice situation was more complex also. And considering the fact that we weren't that precise, I mean, the SBUS correction, the DGNSS correction gives you are within a few meters. So we could be a little bit off when taking those samples. So it's not surprising that we have a deviation. The lighter blue areas are the thinner ice, and the darker blue areas are thicker. You can see that there is a section between at the bottom part of the screen where you have a dark blue area. That was an area where the ice had basically formed a double layer. So if we then talk about areas of improvement, the positioning is one of them. We would like to, and we have looked at using RTK GNSS instead, and to also looked at the possibility of carrying a prism and using a total station if it's a local area that you don't need to fly that far, then a total station might be a solution. There are other things we would like to integrate with. LiDAR is one of them, but there are other things too that we are thinking about integrating into this. Another thing is also that in this project it was a feasibility study, so we didn't spend. If I would do it again, I would collect more data. I would do a higher line density in order to produce a sort of a more complete picture of what the ice situation looks like. But apart from that, I think it worked really fine. The conclusions from this is that it's Airborne GPR and the MALÅ GeoDrone 600 in this case. We were able to successfully map the ice situation near and close to the hydropower plant at a sufficient accuracy. It's something that Vattenfall is at least considering when they are looking at to look at the ice situation around their hydroelectric power plants. I think that Airborne GPR in general is a method that is viable for certain applications, not for all of them, but for definitely some of them. And there is interest from the power companies locally. Many of them, snow taxation, for instance, is one of them. But also other things that I already mentioned. We also have an interest from the people who are doing climate research in Arctic or Antarctica, for instance, when they're planning safe passage routes through a flowing glacier. That's important work also. So there are many, even though it's not a huge market, but it's we have some I think it works fine. So I think it has, and we can improve it further. The accuracy in this particular study were within a few percentages of depth, and I guess that 10% would be a estimate that you could probably assume if you're doing this type of study. I would recommend using navigational control and route planning. It's hard to anything if you can keep a constant elevation above the media that you want to investigate. It is a huge advantage when you get into the processing and interpretation part of your study. Automation and the use of drones for GPR service. is very promising. And I think that automation in particular and use of drones will revolutionize the use of GPR in general. Maybe not airborne, but there will be more of this, and it will come soon. That is the end of my presentation. I'm just going to end with this nice little picture from one of our kickoffs a few years ago, 4 years ago, I think. Saltolokta. Wasn't that so, Andreas?
Yes, indeed, in the far north west of Sweden, actually. So a very exciting place to be. And as you can see, we are very, very happy to be there as well. It was a great opportunity to meet everyone in the company. Thanks a lot for the positive feedback. Really great to have you here. I would also like to take this opportunity to talk a bit about our upcoming webinars. As I mentioned, I have a background in archaeological geophysics, and the next one up is presented by our senior applications engineer, Mike Langton, who will be talking about multi-channel array measurements together with the English television show Time Team. So some new and exciting stuff that's been going on that we are diving into. So, and that is, if I'm not mistaken, the 4th of April. So look out for the announcements. It will be presented through our LinkedIn page and a mailing list. So please look out for that and sign up for the coming sessions. Thanks a lot for connecting. Have a fantastic continuation of the day, and looking forward to see you again